Hello and welcome back to Calculus 3, section 11.8, arc length. We are going to continue the story from Calculus 2. We learned in Calculus 2 that if there is some kind of a curve, f of x, we can find the length of that curve between A and B by working out the integral a to b square root of 1 plus f prime squared dx. That was the arc length integral. So we find the derivative of the function, plug everything in. Now, where did this come from? Well, it actually came from Pythagorean theorem. If you, let me just fill in the blanks over here, b f of b. Nah. So if you take 2 points and you consider the growth in y in terms of x, so this small piece we can enlarge here. I am going to have a curvature of some kind over there, but then what I do is I smooth that out with a straight line. We know that this is the change in x, this is the change in y, and this is the lowercase l, because this is just a representative part. So now if we use Pythagorean theorem, we can write that delta x squared plus delta y squared is equal to L squared, from where L is the square root of delta x squared plus delta y squared. And if you factor out delta x squared, you will have delta x squared factor out, you have 1 plus, and now you have delta y squared over delta x squared. And now this delta x jumps in front of the square root, and this is what we have. So now if you are to plug this into the integral, you have that delta x is your dx, and you have your 1 plus derivative squared. I hope you can see that from the formula. So what is the integral? Integral is infinite sum of all of these small pieces. So we were able to find the length of the line of the arc in one small piece, and now you add all infinity of those, which is integral, and you have the formula which you have seen in Calculus 2. So what you have so far is Calc 2. Now what we want to do is to learn two alternative ways to calculate length of the curve. One of those is going to be parametric form, and another one is going to be polar form. Now for parametric form and for polar form, all we need to do is to do some change of variables, and it should work. It should work just fine. So let's see what kind of substitution and stuff we need in order to convert this. Well, what I'm going to do is I'm going to make this integral to be dt, because we need dt, our parameter is t. or theta, whatever. So let's make it dt. So what I'm going to do is I'm going to take the integral a to b, square root of 1 plus f prime, let's write it as dy dx squared dx, and I'm going to multiply this with a dt over dt. So that doesn't change anything, right, because dt divided by dt is 1. But then I'm going to use these as a unit and leave dt alone over there. So I have integral a to b, square root of 1 plus dy over dx squared times dx dt, and then everything dt. So I just regroup these. Now dx dt is going to undergo square root, and you know that when you are stuffing things in a square root, it picks up an exponent, or square in this case. So we are going to have a square root of 1 plus dy dx squared times dx dt squared, and then we finally have dt over here. Now this needs to distribute to both. You have two terms, right, in there. So we have AB 1 time dx dt squared is dx dt squared, and when I multiply the second two, dx and dx cancel, so we just get dy dt squared and everything dt. That is the formula for in parametric form. You can see that there is a dimension for x in respect to t and another dimension for y in respect to t, and they are separated. So now I can write the arc length formula using parametric form, which is dx dt squared plus dy dt squared dt. What's that? Alright, I can't write. You should be watching the stream, it lags, so... All good?
Well, because of the projector screen is down, so like we're missing the bottom.
Say no more. Thank you. So it was simple manipulation, starting from the formula you should know from Calc 2, and I believe last class you did know it. Multiply by dt over dt and just follow the algebra of, go under the square root, pick up a square and distribute. And there's the formula. So now we can calculate the circumference of a circle, right? Oh, before I forget, A and B are now interval for t, for parameter t. So what am I going to do now? Well, I'm going to say prove the circumference of a circle. This is a cool question for the exam, for instance. So what do we have? We have a circle, radius, let's say 5, and we want to prove that the circumference is 10 pi. Let's go. What I'm going to do first is I'm going to parametricize this and we know that x dimension is going to be 5 cosine t, and the y dimension is 5 sine t. If we switch sine and cosine, then the orientation, the way in which we draw the circle will change, but the circle stays the same. So now, length of the curve is going to be integral 0 to 2 pi, because I want the entire circle, square root of dx dt. All right, now I need to take the derivative of x in respect to t, and that's going to be negative 5 sine t, and then we need to square that, plus take the derivative of the other one, that's going to be 5 cosine t, everything squared, and then we have dt at the end. So let's clean this up as much as possible. The square will kill the negative, so all I have is 25 sine squared t plus another 25 cosine squared t dt. Now, those of you who already know the formulas and did this 5 million times in different courses, you can just skip and say, yep, it's 25, so move along, right? If you don't know what's happening, well, then you will factor out 25, and then you have sine squared t plus cosine squared t to be equal to 1 from before. So now, square root of 25 is 5. I can kick that in front of the integral, and all I'm integrating is 1. So I'm just integrating dt. The integral of that is t, computed from 0 to 2 pi. You get your 10 pi minus 0, which is 10 pi. So we know, right, that the formula 2r pi, or 2 pi r, or whatever order you put it in, so we know that that formula works because we are able to do the proof and show that formula works. So this was 2D, because I only had 2 components, but it turns out to extend this to higher dimension is easy. Just keep adding stuff inside under the root, radical. So you have dx dt, dy dt. Well, you can have dz dt, dw dt, as many dimensions as you want / need. So for 3D, this formula for arc length looks like this: integral a to b square root of dx dt squared plus dy dt squared plus dz dt squared. As I said, you can, put as many of these as you need. Sometimes you need more than 3 dimensions. Well, actually, no, you are using 4 dimensions all the time because of time, right? This location at which you are sitting has its coordinates on this planet, or the universe, whatever. So your location is 3 dimensions of space and 1 dimension of time, because pretty much all of you showed up here 4:30, right? And then if you wait another, I don't know, 10 hours, it'll be 2 a.m. No one would be here, right? So it's important that that dimension is there. So now for 3D, you can extend this to 4D, 5D, whatever, but here it is. And I hope you see, guys, that you have the the magnitude of R inside. So I will show this. We have our vector valued function. This A and B are still in between T. So if you look at the vector notation, let me just first box this. Vector R is given as functions f, g, h, and all of these are functions of time. How do you find the magnitude of the vector? What do? How do you find magnitude of the vector?
Square.
Yes, so that's exactly the formula up there, right? You have all of the derivatives and you just take the calculation and you have it. So in some cases this is useful, in some cases that is useful. Let me just write over here, implies that R prime of t is going to be f prime of t, g prime of t, and h prime of t. Again, all independent. Each one of these is independent, so you have to solve all of them. Good. Let's see if there are any problems that we could solve. All right. So I think arc length calculations, good. Let's do a problem 9 through 16. Pick a number. 14 it is. Nice.